So this is our last set of notes on related rates, day 3. We have 2 examples. We're going to start with another ladder problem. So a 26-foot ladder leans against a vertical wall. So let's get a picture in here. So just like last time, the wall is perpendicular to the ground. The ladder itself is always 26 feet long, so we get to label this as 26 feet since it's constant. Base of the ladder is pulled from the wall at 4 feet per second. So we have a nice rate of change there, feet per second. We need to label the base of the ladder here. So we need a variable here. So I'm going to go ahead and just call it B. So this is my rate of change for B. Now, this time, because the base is moving away from the wall, the length between the base of the ladder and the wall is getting bigger. So dB dt should be positive 4 feet per second. Remember in the last problem with the ladder, the base was pushed toward the wall. So we had to label this value as negative rate of change. So for now, it'll stay positive. So what's the rate of change for the area of the triangle? If you'll remember, we did this last time. We talked about the rate at which the area was changing here. Okay, and so that's what we're going for again. What's the rate at which the area changes? So dA dt when, there's our keyword when the base of the ladder is 10 feet from the wall. So we have our when 10 feet away from the wall. So when the base is 10, so this is my after derivative number. I can't plug that until later. Same thing with any rates of change. So I do need a formula that relates the area of the triangle to its sides. We're going to go ahead and call the height h here. Since as the ladder's base is pulled away from the wall, the top of the ladder slides down the wall, so the height distance here is always changing with time, so we can't actually give that a numerical value. So variables again, and the ladder is always 26 feet long. So let's go ahead and find our area here with the base and the height. 1/2 base times height. So here, in order to do this problem, we're going to take our derivative of each side with respect to time. So dA dt will end up eventually with a dB dt and a dH dt. Notice we have dB dt, we don't have dH dt. In our cone problem yesterday, in 4.3, we were able to make a substitution because we always had a constant relationship between the base, the radius, and the height of the cone. But here, we don't. It's never going to have a constant relationship here, or not one that we have known that we can find. So we are going to use dB dt and dH dt. But what that means is, well, we have dB dt. We're going to have to figure out what dH dt is. So there's another problem that we have to do first. So we do need some formula that does relate the the height and the base to the other side, which is the Pythagorean theorem. So over here on the side, we actually have to start here first. H squared plus b squared is equal to 26 squared. And we're going to do our derivative here. So again, if this isn't obvious, let's just say we didn't notice we had to do this, and we just started by taking the derivative here. And I'll show you where we get stuck. So derivative of each side with respect to time. So we have dA dt, which is what we're looking for. We'll keep that 1/2 as a coefficient, and we'll go ahead and do our product rule here with b times h. So first times the derivative of the second, so that would be dH dt, plus second times the derivative of the first, dB dt. So you see we've got dA dt is the true unknown we're solving for, which means we have to know the remaining values. So when b is 10, we can figure out 10 something 26. We can solve for h. We have dB dt is 4. We don't know dH dt. There was nothing given in the problem that tells us what that is. So that's why I have to figure out dH dt first. So I still have this as an unknown right now. And I needed another formula that related h and b. So here it is. Another formula that just related h and b and no other values like a. So that's just the Pythagorean theorem. Since using 26 as a constant, I won't have a rate of change for that value here. So we'll do our derivative of each side with respect to time over here. And of course, this gives us 2h followed by dH dt plus 2b followed by dB dt is equal to derivative of any number. This is just another number, 26 squared. Derivative would be 0. All right. So we're solving here for dH dt so that we can plug it in here with everything else to get dA dt, the final value we're looking for. So we're going to go ahead and plug in the values that we know from our problem. dB dt is 4. When b is 10, we can solve for h. And then the unknown here, dH dt, is what we're trying to find to use over here. All right. So 2 times h dH dt plus 2 times b is 10. So remember, now that I've taken my derivative, I'm good to use the 10 here. And dB dt is 4. So times 4 equals 0. Now I still need h. So at this moment, b is 10. And at the moment when b is 10, I can do my Pythagorean theorem and find the value of h. But again, this is only to be used once you've taken the derivative. So what value would we get here? This comes out to 24. All right, so solving this, I have 48 dH dt plus 80 equals 0. dH dt then is negative 80 divided by 48, which will reduce to negative 5/3. I do have units for that, of course, as well. Just like dB dt was feet per second, this is also feet per second, since it's the height of the ladder changing with time, feet per second. Why is it negative? Why a negative value? Remember, as the base slides away from the wall, b is getting longer, so that had a rate of change that was positive. As the base slides away from the wall, the top of the ladder slides down the wall. H is getting smaller, so my rate of change is negative. So that's a good thing. Okay, we do want a negative value there. And that's our last value. That's what we needed to plug in over here. So I go back to the problem I started with and plug in the values. So again, b is 10 here in our derivative. So I can now use my derivative values. B is 10. I just found dH dt was negative 5/3. At this moment, what is H? H is 24 times dB dt, which is 4. So that was 2x 4. All right. So from here, we're just going to simplify this. You can use your calculators, and it comes out to 39.66, we'll say 7. And then I need my rate of change, my units, so area over time. So my lengths were all measured in feet, so area is measured in square feet, and time here was measured in seconds, so square feet per second. In problem number 2, we are going to start with a 5-foot-tall woman who is walking away from a 20-foot high street lamp at 6 feet per second. So a 20-foot tall street lamp and a 5-foot woman walking away from it. So walking away 5 feet. So these are constant values, so we're going to label them as constants. They're not going to change, the lamp and the woman's height. And the first question we're asked is, how fast is the tip of her shadow changing? When she is 14 feet from the street lamp. All right, so a few things here. We're asked about the rate at which the tip of her shadow is changing. Rate at which the tip of her shadow is changing. So the tip of her shadow over here is based from the light over her head down to the ground. So the tip of her shadow is this entire length here, okay, x. So we are trying to find dx dt. Okay. We're given information about how fast she's walking away from the street lamp. So her walking is going to be this distance here between her and the street lamp. So this is W. So what they gave us here, dW dt, is at 6 feet per second. So we need some sort of equation that relates x and w together. Well, this is missing a little bit of information. This length right here of w is not part of one of my triangles here. Okay, I have these two right triangles, and these triangles are similar to one another. So I have the street lamp's height 20 is to x, as 5 is to this small distance here. So this distance right here should be x minus w. So that's going to be our equation that relates x and w together. So we have 20 is to x, as 5 is to x minus w. All right. So we can simplify this before we take the derivative. Let's go ahead and cross multiply. We get 20x minus 20w is equal to 5x. Or we can write that as 15x is equal to 20w. And we can even simplify by dividing out by 5 on both sides. 3x is equal to 4w. Okay. And then we have our rates of change here, so we're ready to take the derivative of each side. And remember, we were given a when statement here, when she's 14 feet away from the street lamp. So when her distance away is 14 feet. We're not going to use that until we've taken the derivative. So let's do that then. So on the left, we have derivative of 3x is 3, followed by dx dt. On the right, derivative of 4w is 4, dw dt. We are solving for dx dt, this value here. We know dw dt is 6, so we'll make that substitution in. And notice, I never have a time that I need to plug in this 14 when she is 14 feet away from the lamp. So I don't have a value of w in the problem to use. So this is simply dx dt is equal to 4/3 of 6, which is going to give us 8. And this rate of change of distance over time is feet per second. So apparently it didn't matter how far away she was from the street lamp. The rate at which the tip of her shadow is changing is always going to be 8 feet per second. One more question in this problem. This one says, at what rate is the length of her shadow moving? So the length of her shadow is between, well, her feet to the tip of her shadow. So that length is x minus w. So the length of her shadow, x minus w. And we want to know at what rate it's changing. So the derivative of x minus w is going to give us just dx dt minus dw dt. All I did was take the derivative of x minus w with respect to time. You'd get a 1 here, dx dt, minus 1 dw dt. So just dx dt minus dw dt. dx dt is what we just found in the part A of the problem, which was 8. dw dt was given to us as 6. So this comes out to 2 feet per second. And again, this wasn't based on how far away she was from the street lamp, so that number didn't matter.